Hello and welcome back to this seventh video or lesson of Introduction to Trigonometry. And in the previous lesson, we discussed and we stressed the importance of not thinking of sine and cosine as values where you can use the distributive property, never ever. And we put some restrictions on, after you go through the gap between grade 8 and grade 11 and 12, and then you learn your laws of sines and cosines in grade 11 and 12, we said that the restriction is for you to start with the law of cosine if you have the three sides. And if you are to find an angle, to start with the largest angle, and we explained why. We said that, remember that? Here, let's go here. We said that we start with the largest angle, whether it's acute or whether it's obtuse. We start with the largest angle, and we always have to consider the side adjacent. If we call that angle A, this is small side B. We have to always consider the angle, the side adjacent to that angle. And we're going to study that side adjacent to the angle that we calculated in regards and compare it to what? To the side that is, on the across from that angle. So if this is A, big A, this is side A. So if this adjacent side B is smaller than A, then yeah, by all means, you have one solution here in the obtuse. And in the acute, we said if A is, larger than B, there could be also a situation where A equal B, and we have an isosceles. And we studied the ambiguity that is caused by just, putting yourself in the situation where I want to start with the law of sine, because you don't know which one is the largest. In the law of cosine, you know which one is the largest because you're given three sides, so you can pick. And if A is the largest, then you start with angle A. If B is the largest, you start with angle B. And we said unless you are told start with the law of sines, because they probably tested it and they know what they're doing, they want you to just use the law of sine, see if you know it, then you just start with the law of cosine. All right, okay. And then we also explained the areas in an oblique triangle, and we said this comes from the same concept of the area of a triangle, which is half height times base. And I believe I still have it here. We did it half times base. Yeah, right here. And we said if this is an oblique triangle, and we can, and if we want to consider A, we can consider any side, either side, as your base. If A is the base, I draw a perpendicular from vertex A all the way to base A, and this is my height. And I go ahead and I just fulfill, and I write what I know, what I learned in middle school: area equal half of height, which is in this situation what? Sine of C. See that triangle, right triangle that we formed when we drew the perpendicular? We formed a right triangle where if we take sine C and we compare the opposite side, which is the height, the altitude, to the hypotenuse, which is B in this situation, we get H equal B times sine C. And our base is A, so area is going to equal half A times B sine C. And we said it's always the case if you take the other two. BC, the angle between them is A, so it's sine of A. AC, the angle between them is B, so it's half AC times sine B. And again, there is nothing here to memorize. It's just your old area of a triangle equal half height times base. So far, even the law of sine and law of cosine, when we get to them, we're gonna explain them in details, and we don't need them at all. Then we started studying the angles of depression and the angles of elevation. We said it's just something very simple. If you're standing, still on ground or on top of a lighthouse and you're looking down, that's the angle you're forming with the horizontal x-axis is your angle of depression. If you're looking up at a bird, the angle you're forming with the horizontal x-axis is your angle of elevation. And I gave you an example, a real-life example, or you can have both together. If you're standing, in a high-rise or in an apartment building or in your house, on a ground level, on a one-story house, and then you're looking through the window, you can look down and you can look up. The guy was standing in his hotel room or through the window, he was looking up and down at a high-rise or at an apartment building across. And then we had to measure the distance between where he was standing, his window, his hotel, his apartment building, and the apartment building where that crime happened. And then, of course, we just calculated the distance. The rest is police work and investigative work and forensic science work. Okay? And then the last thing we talked about, and this is where we're going to start right now, is we don't really need the angle. If we, because we can use something called the inverse. And the inverse, the same way we use the angle to get that ratio, the breakup of the vector in the horizontal component compared to the total force or the total vector or, the hypotenuse gives us a certain ratio. We said like sine of 30, this angle gives us a ratio of 1 divided by 2. So what is, if we take the inverse, what is the ratio that gives us an angle of 30? It's 1/2. So if we take the inverse of this, in math it's called arcsine, or sine of -1 of your ratio, we get back an angle of 30 degrees. We're going to dig into that a little bit deeper now. But before we do that, we're going to go back to the angles of elevations and depression and understand that with the tangent, we also don't need the hypotenuse. We explained that. I'm going to go back to the same example. I'm going to consider that I have a lighthouse here, okay? And then the person on top watching the boats with an angle of depression, and we're not going to give the angle. It's going clockwise in this direction. I'm going to give the x. I'm going to say this is the boat, and he's 52 feet. The boat is 52 feet. It's 52 feet away from the lighthouse. The lighthouse, we're going to make the height of it, the altitude is 40 feet, the same. So in a situation like that, my tangent, theta or alpha or whatever you want to call the angle, is opposite side, which is 40 here. This is theta, right? Tangent theta equal opposite 40. This is your opposite, right? 40. The reflection on that vertical line divided by what? By 52. This is the adjacent right here. The reflection here, 52. So this is my 52. And if we do the math, 40 divided by 52 is something around 0. Let me do it here. 0.74 or 76. Sure, 40 divided by 52, 0.76. So I have a 0.76, okay, and then, and this is of course less than 1, so that's perfect. You're doing the right thing because all of them, including the tangent and the cotangent and the cosecant and the secant, they have to be between -1 and +1. We're going back to graphing them in a few minutes, okay? So this is the ratio. What is the arc tangent of this? So because I want, the arc tangent of this ratio gives me what angle? What angle was able to give me that, I have to find the inverse. The inverse is around the y equal x, the identity function. We're gonna go into details again in a few minutes. So just remember, I'm doing an inverse. The same way I swap the x with the y's and I solve, and we're going to go back to that and explain it with a simple linear equation, y equal to x plus 1 or something like that. So this is something that you need your scientific TI-84 or whatever it's called calculator to calculate. And then you just plug it in, arctangent of 0.76, and you get it in radian. And let me see here, 0.649 radian. Okay, so now I have the angle, and I didn't need any, I didn't need the hypotenuse. All I needed was my scientific calculator when you are allowed to use a scientific calculator. And you just needed the opposite and the adjacent side, okay? Now, in order to convert it, you just do your regular. You stack them up like this. You have your radian, we said 0.649, and you just find the fourth element. And in this situation, you don't need a scientific calculator here, 37.2 degrees. So 37.2 degrees. So that's my angle. So sometimes the tangent is the best way to look for the angle. If you have your scientific calculator, you don't need the hypotenuse. That's the whole point. And then you just jump into opposite divided by adjacent, and then you find your arctangent. As far as arctangent is concerned, before we talk about arctangent, let's keep in mind that an inverse function is basically, it gives us back the angle. It's the function that is the reflection of the original graph over the line or the identity line, identity function y equal x. So if you have something like y equal to x plus 1 from middle school, this one also needs a restriction. Remember, any function needs a restriction to be a function in order not to repeat the x. It has to pass the vertical line test like this. This one passes the vertical line test. There is one, it only passes through one. But does it pass the horizontal line test? No, it does not, because it crosses at two different points. So this one, we cannot, find the inverse of this one unless we restrict its domain. We're going to go back to the explanation of that, but first I need to remind you what and how to solve for if you have y equal to x plus 1. I call it SS, meaning you swap and then you solve. So basically the first thing you do is you swap. So instead of y equal to x plus 1, you do x equal to y plus 1. And then you need to solve for what? For y. So you put y on one side, x on the other side, minus 1. And then y equal half x minus half. And that's how you swap and then solve. So it's called SS. There is nothing all you need to remember here and not memorize, the inverse is the reflection over the identity function y equal x. Okay? That's all there is to it. And the same, we're spinning out the angle by doing the same thing. Instead of swapping, there is no x and y here. Remember, we took that segment length out of the rotating vector that is not motionless, and we animated this segment length. But this segment length is actually a fraction, a ratio of x comparing to the hypotenuse, or y vertical component of the vector compared to the total force. So basically we're taking an angle and we're coming up with a ratio. So the angle is your x and the ratio is your y. So if you take your y, you swap it, you should get back the x, the angle. That's all we're doing. So the tangent of an angle equal your ratio, your y. So tangent of x equal y, okay? So we don't call it tangent when we swap it. We call it tangent minus 1. That's all you need to just conceptualize. Or arctangent. I prefer the arc. We will talk later why arctangent is better. So you have two ways you can, call this in math, or you can label it. Tangent minus 1, or, to the power. It's not really, I'm sorry, it's definitely not to the power minus 1. Tangent that's why I like to call it arctangent, because this is totally different when you say to the power minus 1. It confuses a lot of students. Okay, so it's arctangent of what? Of the ratio of y. spits back and gives back the angle x or theta or alpha or whatever you want to call it. Okay, so if I have, what's the arc, what's the tangent of 45? Let's do an easy one. Tangent of 45 is what? Is square root of 2 divided by 2 opposite divided by square root of 2 divided by 2. So it's 1 in quadrant 1. So if I want to do arc tangent of this ratio, square root of 2 divided by 2 divided by square root of 2 divided by 2 of 1, which angle do I get back? 45. That's all I'm doing. But this is a very tedious mathematical calculation. That's why you need your scientific calculator for this one. But all you need to do is just understand the concept. The same way we swapped x and y, we're swapping the angle and the ratio, okay? And the ratio is basically your sine and your cosine. We explained that now after 7 lessons in 7 hours. You should know that sine and cosine are basically trig ratios, okay? We're comparing this horizontal and vertical component to the total vector, to the total force. Now, let's see. Okay, yes. We're restricting the domain. So basically, let's go back to our easy, if we draw something like that. And your y equal x is right here. And I come and I draw y equal x squared. An easy y equal x squared. Okay, x to the power 2. Now this one passes the vertical, line test. Okay, so it is a function, but it doesn't pass the horizontal. Again, this is the restriction line test. So I cannot find a reflection for it. Think about it. How can you find a reflection of something like that in a coordinate 2D plane? You cannot imagine it here, swirling in a 3D dimensional plane. In a 2D plane, how can you find, the reflection over this y equal x? It's not really, practical. It's very impractical to do it. So basically what we do is we restrict the domain. We say the domain here, we're gonna restrict it to what? Not to minus infinity plus infinity. We're gonna make x greater than or equal to 0. Then, so I don't take this side. Then we can pass the horizontal line test. And then if I do that, what happens? If you do that, you can find your inverse, and your inverse becomes, something like that. The inverse of this section over the y equal x, I can find it. So I basically restricted the domain. And when I restricted the domain, this domain becomes what? The domain becomes the range of the new function, of the inverse function. And the same thing happens with the sine and the cosine. But before we dig into that, restricting the domain for the sine and the cosine, let's first review the sine and the cosine. We said, we take those segment lengths, out of the tip of the vector makes these red. Review video number 2 or 3, 2 and 3. These small tiny red dots, they make, the tip of the vector might make red dots as it moves within this first 2 pi or 360-degree cycles. For the sine, they make them on the vertical y-axis. We remove the segment length and we study them. We make an animation for them. And we come up with this wave or sinusoidal wave function that looks like this. But since they are between -1 and +1, I do have a range between -1 and +1. So that's, if I go like this, I do have my -1 here, and I have my +1 here. And then what do we have here? You have your 0 here, and you have your pi over 2 here, you have your pi here, 3 pi over 2, and then 2 pi. This is the first cycle. We call it the normal cycle, where, we finish as one cycle. What does that mean? That means your sine function, remember when it's pi over 2, it goes all the way to 0, 1. Goes here, and then when it goes to pi or 180 degrees, it goes back to 0. Sine of pi or sine of 180 degrees is 0. When it's at 3 pi over 2, it's right here at -1, and it goes back to 2 pi. So this is y equal sine of x, okay, a simple one within a cycle of 2 pi. What does that mean? That means, remember, we said it's one time, f equal one time, one cycle in one period. The period could change, but when the cycle is the normal cycle, that's your 2 pi. So this one time is 2 pi divided by the p, okay? Now, the thing is, in most books, and remember, because we said the y, the sine and the cosine are functions of, it's a function of frequency times time. Frequency times time. It repeats the same pattern in different, intervals of time. So it could be, it could be in 2 pi, it could be in pi, it could be in 4 pi, it could be in 6 pi, it could be, in pi divided by 4. It depends. But the normal one is this one, y equals sine of x. There is no stretching, no squishing, no pulling, no extra amplitude in the horizontal or in the vertical direction. We're not pulling or tugging this way, and we're not pulling. This is your normal function, where the normal cycle, the one time, the one cycle is 2 pi. Now, in your books, in most textbooks, because we're not studying physics, because we're not, they don't relate it to you as a function of frequency times time, and they want you to, they want to make it easier for you, because they call, when they have something like y equal to sine of x, they call this too the a, or the amplitude, or the big A. They call the f, or the frequency, a b as a coefficient. So it's basically, you're going to see that b, or frequency, f equal b, it's the same thing, equal 2 pi divided by the period. So the period does change, okay? If the frequency is, higher or lower, and we're going to study that. But for now, let's just stick to y equals sine of x. We will get to those by the end of this lesson. So this is your regular y equals sine of x, or y equal frequency times time, okay? And in your books, we're going to keep repeating this. Frequency is referred to as the big, letter B, capital B, okay? Now, the cosine, yes, and for the sine, you need to know that the domain is, x is r, or real numbers, and the range is between, y is between y minus 1 and plus 1. You should know that by now, okay? Yes, at y equal, at x equals 0, that means, the sine wave is not really moving. So as if you're on a beach and you're on the shore, the sine is on the shoreline at x equals 0. What else should we, I believe that's it. It's very self-explanatory, after you understand that you pulled it out of that, you pulled out the segment lengths and you animated them. That's your y equals sine of x, with no stretching, no squishing, and no amplitude. Now, y equal cosine of x, y equal cosine of x goes like this. We have the same domain, so we have our minus 1, and then we have our plus 1, and then of course this is the pi over 2, this is the pi, 3 pi over 2, and this is the 2 pi. Okay, and then at x equals 0, the cosine is 1. It's 0 at pi over 2, and then at pi it's minus 1. 3 pi over 2 is again a 0, and then it goes like this. So this is your regular cosine, y equal cosine of x. And again, the domain x equal r, and the same range between minus 1 and plus 1. At x equal 0, this cosine, if you're calling it a wave, a sinusoidal wave, there are no, at x equals 0 right here, it's not that there are no waves. It's like, you're jumping off the cliff. You're going into maybe, the deep water, if you want to think about it this way. Other than that, again, this one is self-explanatory, and it is a function of frequency and time. Y equal cosine of frequency times time. And we're going to find out that this frequency, we already studied that it's one time, one cycle every period, like the washing machine, remember? And this period is the one that changes, okay? And in a normal situation, this one time is 2 pi. So it's 2 pi divided by p. But, in your most books, this f is referred to by the capital B. Now, that being said, we're going to leave that for a second before we dig into the B and the big capital B and the amplitude, the big A. We're going to go back to the inverse function. We said that the inverse function of y equal sine of x, okay, and we need to restrict that. Why do we need to restrict that? The same way, because if you look at that, it's going to keep repeating itself. Goes here, and then 0 here, and it keeps repeating itself. How can you fathom or, conceptualize in a 2D dimensional plane or a coordinate plane, a reflection of that over the y equal x? You need to restrict it. This is just common sense. So where do we restrict it at? So if I really look at it, the best way to restrict it is you remember the unit circle where r equal 1? It's to restrict it at the 1, so at the pi over 2 and the minus pi over 2. So between pi over 2 and minus pi over 2, or I'm sorry, minus pi over 2 and plus pi over 2, I'm going to restrict that. So this is going to be my domain. What does that mean? So if I am to draw y equals sine of x, this is the 2 pi, this is the pi, this is the pi over 2, and this is my minus pi over 2, okay? Because I want to take it, from both ends, before the 0 and after the 0. So a regular y equals sine of x goes like this, right? It goes like 0 here, minus 1 here, and it goes like this. And it goes again, at minus pi over 2, it's right here at minus 1. So I'm going to take that stretch from here to here. And this one, if I just conceptualize it, if I imagine it, this is my y equal x, I want to find the reflection over that y over x. This reflection is going to give me back and spits back the angle, because the sine, it's going to repeat itself. It's a frequency, remember? So I don't need to look at the whole frequency. It is the same frequency. Now it changes. It could be compressed, it could be squished. The period can change, but it's the same pattern, the same cycle. So that's why I can restrict it, okay? Again, just common sense. Now if I'm going to draw, if I write y equals sine of x, and I write my domain as minus pi over 2 plus pi over 2, I want to restrict it. This domain becomes the range of the arc sine of f of x, which is, arc sine of x, or sine of minus 1, not to the power minus 1, sine is minus 1x. Always better to say arc sine, okay, because this is not a power of minus 1. Again, so if I am to draw that, look, let's make the drawing just between minus pi over 2 and plus pi over 2. So if I am to go like this, okay, so if this is, let's say this is my 1, okay, and this is my minus 1, and this is pi over 2 should be somewhere here, because this is 3.1415. It's a little bit more than 1, okay? That's all I did. For those of you who didn't understand why I put it here, this is your plus pi over 2, and this is my minus pi over 2. Now, this domain became what? Became the range. So now I have to also put it here. And this is the plus pi over 2, and this is the minus 1, and this is the minus pi over 2. This is your y equal x, okay? Now, where is the original? The original goes from here to 1 right here. And then goes to a minus 1 right where, here, this is your original, okay? Now, so if I am to draw the other one has, this is the restriction. So this one becomes the range, okay? And it has to be 1 right here at the x-axis. So I go like this, and the restriction goes all the way to minus pi over 2 and minus 1 right here. So that's the, like this. So this is my arc sine. Y equal arc sine of x, of any x. But I had to restrict it because it's the same pattern. You cannot just, take all these folds of repeating waves and pattern and imagine that you are, imagine a reflection over the y equal x. That's why we did restrict it. And why minus pi over 2 and plus pi over 2? Because remember, let's look at the circle. Look, it's not the unit circle, it's any circle. The first rotation, this is your pi over 2 minus pi over 2. This is the max that this rotating vector can go to, in the vertical direction. The max that it can go to in a vertical direction is plus 1, x 0 y plus 1, 0 plus 1 to 0 minus 1 at the pi over 2 and the minus pi over 2. And this is, when we say this is the max, that means this is the maximum alteration, or, this is the maximum factor that can interfere in this breakup, vertical breakup in relation to the total vector. There is, this is the max. After that, we get an inclination. And then we get an inclination all the way to go to the negative minus 1. And then we go back to 0. We complete the first rotation or the first cycle, which is the 2 pi. Okay? So that's why we chose pi over 2 and minus pi over 2. Minus pi over 2 and pi over 2 is gonna repeat over and over and over and over. Okay? Very common sense. We didn't choose the 0 and the pi because the sine is actually 0, at 0 and 180 degrees. Okay? Now, if we go back and we have our restriction now, we can, we're going to repeat this. We're going to do the inverse also of the cosine and the inverse of the tangent when we study the tangent and how we draw the tangent. But just know that there is a restriction for the arc sine, and simply because, it's common sense, and because it's, like we said before, it doesn't pass this horizontal line test. Now, many of you maybe didn't, don't remember that, but it doesn't really pass the horizontal line test. So, if you cannot remember that, just remember your simple y equal x squared, or x to the power 2. It doesn't pass the horizontal line test. That's why it doesn't have an inverse. That's why I have to restrict it like this and forget about this part in order to make a reflection over the y equal x. Same with the sine, same with the cosine. They don't pass the horizontal line test. And, it's even more than that. It doesn't make any sense. It's repeating. It's a repeating pattern. You cannot, imagine that all these reflections, could be in the hundreds, in the thousands over y equal x. You just restrict it to the first one, to the original one, in the first circle, that goes your higher factor, the highest factor that can affect this ratio is 0 plus 1 and 0 minus 1, where the angle is minus pi over 2, and plus pi over 2. That's it. That's all we need to remember. Now, before we go into, let me see what else. We need to go into the amplitude and the frequency and the phase shift. Before we go into that, we just need to recap all the formulas that we didn't really memorize so far. So far, the amount of rotation of this ratio, the vertical compared to the total force, plus the amount of rotation squared of the horizontal component divided by the total force equal 1. We all agree on this. And we also studied the two special triangles. And we said this is my, if I can go like this is my 60, this is my 1, this is my 2, this is my square root of 3, this is my 30. And the other special triangle is the isosceles 45, 45, 1, 1, and square root of 2. And we also did, I showed you special triangles, the 3, 4, 5 triangle, remember that? And then we said, we can just go ahead and, if you just multiply it, this one becomes a 6, 8, 10, 6, 8, 10. It could become, if you 2 times 3, it becomes a 9, 12, 15. This is when we first started within the force, the kicker, the soccer player kicking with, and we multiplied by 3 from here to here. And we said the ratio stays the same, okay? Because 3 divided by 5 is the same as 9 divided by 15 equals 0.6. So, and with this idea of 3, 4, 5, there are other special triangles that, with time and with exercise, you should remember. It's not only, it's also the 5, 12, 13, which if you multiply, let's say by 2, becomes a 10, 24, 26. And there is also the 8, there is a 7 first, 7, 24, 25, and there is the 8, 15, 17, 8, 15, 17, and there is the 9, 40, and 40. Now, how do I remember them? Just exercise. Remember, if you're studying with me, I urge you to do arithmetic, mental arithmetic every day, 5 minutes, math, simple math operations, simple math chains. What is 18 times 18, what is 14 times 14, what is 16 times 16, what are my special triangles, percentages, ratios, scaling. So this comes with time. You're not gonna, I don't sit down and memorize these, the 5, 12, 13, 7, 24, 25, 9, 40, 41. There is no one for the 4. There is no one that starts with the 4. It's 3, 4, 5. And then there is no one that starts with the 6. The 6 is part of the 3, 4, 5. Okay, that becomes 6, 8, 10 when you multiply by 2. Okay, that's how I remember it. There is no one that starts with the 4, no one that starts with the 6. Okay, now with all that being said, there is also the TSC, the special hexagon that gave us many functions that we bypass the memorization. Remember, once you remember that it's a hexagon and it's called a TSC, tangent, sine, cosine, and this is my cofunction, they go across. And we said linguistically, I learned that, I didn't know that, a long time ago. I learned that secant equals last, and it's the same in French. I learned it in French, and cosecant means next to last. I believe that that's a Latin, it has a Latin origin. Anyway, and we said, like, if that means sine of 15 equal, because it's across, it's a confunction, it's equal cosine of what? 90 minus 15, so cosine of 75. If I am to look for secant of 40, it's going to be equal to cosecant of 90 minus 40, which is cosecant of 50. Okay? And we said that we can go clockwise and counterclockwise, and that's the beauty of it. So when we're simplifying, when they give you in grade 9 and 10, when they give you these big simplify these trig functions or trig ratios or trig fractions, and then you're like overwhelmed, just go back to your TSC hexagon or magical hexagon or whatever you want to call it, and you can go clockwise or counterclockwise. you know, I don't remember, you know, I don't memorize any of that stuff. So cosine is actually cotangent, if I go this way, divided by cosecant. Okay, so, and then, you know, if I want to go the other way around, secant equals tangent divided by sine. So that makes it very easy, breaks down a lot of things for us. Now we can also do the clockwise and counterclockwise, and we can do the product identities, remember? So if we go like that, we can even do them with the one that is in the middle. So you connect the vertices. So always one in the middle, and sine, cosine, cotangent, cosecant, and secant here, and the famous tangent right here. And what do I mean by that? Means, you know, the one in the middle, the product, this is in the middle of what? Of this and this, equals what? Equal tangent times cosine of any angle. So sine theta equal tangent theta times cosine theta. And then if you want to come to the one in the middle like this, you can say tangent theta or tangent x times cotangent theta equals 1. It's in the middle. Or you can say, you know, sine theta times cosecant theta equal 1. Look, 1 is in the middle of them right there. And this is how we got our reciprocal identities. Cosecant being what? Cosecant being 1 divided by sine, or sine being 1 divided by cosecant. And that's why the sine is related to the cosecant, and the cosine is related to the last part, to the secant. Okay? So what else did we do? Again, nothing to memorize here. We're gonna even dig now deeper in the next lesson with frequency and the amplitude, but, you know, again, so far the memorization is left for something, you know, with some double angle identity and sum identity and product identities. I didn't explain those yet. Those are gonna come, you know, with the details later, but I just explained that, you know, something like that, sine of u plus v, there's no distributive property. You go sine u times cosine v plus cosine u sine v. And then we said that stuff like that, we're going to study it later, and we're going to understand that the sine and the cosine, they're like partners, lobster lovers, you know, they stick together. The cosine is greedier. When you have something like that with the cosine goes with the cosine of u stays with the cosine of the v, and then it changes the sign, and it gets rid of the sine. So there are many ways that I can help you minimize this memorization to, you know, to a very, very, very small numbers of laws and formulas. Okay, now what else did we learn here? We did the pi over 2, we cofunction, reciprocal. Yes, the last thing I'm gonna remind you of is the 3 special triangles that we said exist inside the TSC. And those are super, super important. So this is my sine, this is my cosine, this is my cotangent, this is my cosecant, this is my secant, and this is my tangent. Okay, so the first one, this is 1 here in the middle, is this one, and then you have this one, and you have 1 here. The first one gives you what? If you go like this here, gives you sine square of angle amount of rotation theta x, whatever it is, plus cosine square theta equal 1. This one gives you what? This one gives you 1 plus, because we start with 1 here, 1, and those you're going to use a lot. 1 plus cotangent square theta equal cosecant square theta. And this last one you're going to use a lot. You're going to see it in a lot of simplification when they tell you simplify. Tangent square x or tangent square theta plus 1 in this last one here equal secant square theta. Okay, with that, you know, we pretty much went through the basics of all those function, co-function, and identities, and product identities, and reciprocal identities. We're going to leave the half angle, the double angle, the sum, and the difference identity to later when we dig deeper after we finish with this helicopter overview. Now, the last thing we're going to do here, actually, before we go into amplitude and frequency again, we're going to talk about the odd function. I'm sorry, let's go back here. We're going to talk about the odd function. Come on. Here, let's go back to a new one here. Here. Okay, we're going to talk about the odd function and the even functions. The sine and the cosine are to be thought of as odd functions and even functions. What do I mean by this? Now, if you have something like that, and I always like to take the y equal x squared because it's an easy function. If it goes like this, and you do f of x equal f of minus x, you are actually looking for the reflection of this one over what? Over the y-axis. So if you do something like that, you're looking for the reflection over the y-axis. And then if you have something like this one, here. If you have something like this, make it easy again with the y equal x squared, something like that. Here, if you do like this, minus f of x, so you're doing the reflection over what? Over the x-axis. And the reflection looks like this, something like that. Okay? So when it's equal minus f of x, minus the whole sketch or the whole graph, this is a reflection over actually the x-axis. When it's equal f of the minus x, so the minus goes inside, it's a reflection over the y-axis because we are going into negative axis. See the negative axis here, the negative territory? So that's why it's minus x. But when we talk sine of and cosine, are we really doing this? We're actually not doing this. We're, some students think like, for example, we gave the example, this example. We're actually doing odd and even function that is totally different than that. If we say find the sine of minus 120 degrees, okay? You come and you tell me, oh, you taught me that I have to go clockwise, correct? So I go clockwise and I end up, and I have to look for location, I end up here. This is my minus 120. I say correct, okay? And you tell me, okay, you said quadrant 3. I don't want to memorize, so quadrant 3, I have to measure this reference angle in quadrant 3. I say, okay, measure it from the tip of the angle. What's left here? 60. Because if you go 120, so you are here where? You are at 240. Okay? So this is 60. But it's in the negative because the sine is negative here. The vertical component is in the negative area. So equal minus sine of 60 degrees. And that's equal minus square root of 3 divided by 2. I say perfect. You tell me, okay, then this is something similar to what? No. Keep going. Do it now in quadrant 4. Quadrant 4. Do sine of minus 60 here. Sine of minus 60 here, if you just go minus 60 from here to here. Sine of minus 60 going clockwise in quadrant 4, it's still, minus sine of 60 because the vertical component is in the negative. So it's still minus square root of 3 divided by 2. So for the sine, it's working. However, let's do it for the cosine with the same number. Let's do cosine. And let's do cosine of minus 120 degrees. Again, what do? I come clockwise and I end up here. If I come clockwise and I end up at the 240 in quadrant 3. And in quadrant 3, I take the tip of the vector and I draw this perpendicular and I get my reference angle. And I get my reference angle, you know, in here, which is 60. So cosine of minus 120 equal cosine of 60. Or is it? Equal minus cosine of 60. Because you are in quadrant 3. So here we're following the location. We're not really following a reflection over, you know, the x-axis and the y-axis. Please don't confuse that. You know, I had a few students who were confused with that. Here we're not following the reflection over the x-axis and the y-axis. We're just following the location, the quadrant. Because if I go, look at this, minus 60 here, cosine of minus 60 equals what? Equal plus cosine of 60 now. Equal plus a half. Okay? Cosine of minus 120, the cosine is negative here. But the cosine is positive in quadrant 3. So I'm just following the quadrant again, the location. I'm not doing any reflection here. The only thing I am doing is an even and an odd function. Now, why even and odd? And what is even and odd? I'm just going to remind you, we're going to start that in the next video, in the next lesson. I'm just going to remind you that about the definition of even and odd. The definition of an odd function, that means f of minus x equal minus f of x. And this means it's symmetric about the origin. It's like y equal x cubed. It's like f of minus x squared equal minus f of x squared. It's symmetric around the about the origin, around the origin, okay, which is 0, 0, your origin in a coordinate plane. So this is an odd function symmetric about the origin, where f of minus x, that means if you take x and y, you know, you're gonna spit them out as minus x minus y. So the y does change to minus y. This is an odd function. And that's why the sine follows an odd function from the example that we just gave. We're going to repeat that in the next video. While the cosine does not follow an odd function. It follows an even function. If you look at the graph of the cosine that we just did, remember that graph? We sketched the simple cosine and we said this is my 0, 0, okay, and this is my minus 1, this is my plus 1, and this is, let's say, the pi minus pi over 2, this is the plus pi over 2, and this is the pi, this is the 2 pi, and the cosine goes like this. At pi over 2 it's 0, and then here it goes like this. 0 again, it goes like this. And on the other side, look at it carefully now. It goes through that minus pi over 2 like this. So if you look at this function actually gives back the same y. Look at the y. The y is the same here and here. The y is the same here and here. The y is the same here and here. So the cosine is basically an even function that is symmetrical or symmetric about or around the y-axis. Okay? So the cosine function is an even function. That means if you have an x and a y, you spit back a minus x, but the same y. So the pi over 2 goes to minus pi over 2. So the x changes to minus x, however the y stays the same. And I was able to tell that just by looking at the graph. Okay? If you graph it And you're restricted again because you don't want to look at it, continuously. It can go on forever, 2 pi and 200 pi and 2000 pi. So I restricted that between minus pi over 2 and plus pi over 2 and minus 1 and plus 1. And I looked at it. The x becomes a minus x around the y-axis. However, the y remains the same, okay? It's very obvious. There is nothing to memorize here. So all you need to do is just conceptualize in your brain this cosine function. Cosine function, the x becomes a minus x, but the y does not become a minus y. It stays y. So it's an even function, which means it's symmetrical or symmetric around the y-axis, the vertical y-axis in the coordinate plane. However, the sine, the x becomes a minus x, and the y becomes a minus y. And again, if we conceptualize it, it's very obvious. Let's look at it here.